Welcome to the video presentation for the backend design of a 5.4 design with special focus on clock tree synthesis. So this project is done as a group of 3, including myself, Melvin, and my team members, Saurabh and Nancy, who will be joining in later. So these are the topics that we have covered as a part of the clock tree synthesis process, and these are the general specifications that we are supposed to meet. We have chosen an RTL meeting all these conditions, which is the 5.4 design, and we have to meet the timing specifications 1 to 5, the area and floor plan specifications 1 to 3, the shorts and opens, and the the formal equivalence verification using the conformal tool. So we'll start with DC, where we'll convert the RTL design of the 5.4 design, which is in system Verilog, into a netlist. So I'll be doing the commands and explaining them as I run them. So first we'll open DC shell. Okay, so this brings up the DC shell, and my 5.4 design is present at the folder which I'm typing in. So this is the system Verilog, the RTL code for the 5.4 design. So I need to run that corresponding tickle file which converts the SV design into netlist. So the tickle file is present in this folder. So I source it, I run it. While it is running, I will have a quick go through that particular tickle file. This is the location, and this is the FIFA.sv RTL file, and this is the tickle file that we are currently running in the background. So this tickle file consists of the commands that convert the RTL file into the netlist file. So this command appends a search path to look in this particular folder where we have defined the models required to generate the netlist. And this one, set link library, is a command where we are setting the link library. For this design, we'll be using an HVT model with a threshold of 0.95 volt, and which is supposed to work at a temperature of 125 degrees Celsius. And the link library defines the name of the library that refers to the library of cells used solely for reference. That is, the cells in the link library are not inferred by the DC shell. So basically what you mean by the link library is that it is a library you use components from for making the RTL the netlist out of the RTL design. And after that, we are setting the target library. The target library specifies the name of the technology library that corresponds to the library whose cells designers want DC or ICC, which we will be using later, which the designers want to infer and finally map it to. So this is the target, and this is the link library that we are setting right now. So the difference is that the target library is the library you synthesize for, and it contains the gates that DC uses to map gates from the input to the output netlist. So after that we are analyzing the SV file. This is the DC command which analyzes our SV files, and then we are elaborating it, which is currently happening in the background. Probably it is finished in the meantime, and along in the same tickle file we'll be creating the clocks that we'll be using for the FIFO design. I've created 3 clocks: W clock, R clock, and W clock 2x, with and considering one of the clocks declarations, the period, the number after the period corresponds to its period, and this corresponds to the transition or the falling edge, the rising edge, falling edge of the clock. And in order to meet the specification, the general specifications, we have chosen the 3 clocks periods to be as you can see. This corresponds to 1 nanoseconds, this corresponds to 0.666 nanoseconds, and W clock, the WCLK2X will be half of it, which is 0.5. And in the DC we have set the constraints that we are supposed to put here to meet the timing specification, where the cycle time is 1000 picoseconds or better, and all inputs are available after 2/3 of cycle time. All outputs are needed before 2/3 of cycle time. The first constraint is being met by creating the clock with the period as specified. The second and the third constraints are put by these commands, where we specify an input delay such that it is greater than 2/3 of the corresponding clock's period, and same goes with the output. And in order to meet the transitions, that is the specifications, the last 2 specifications, we have used set max transition so that the input transition criteria are met. So the reason we are providing it in the DC providing the tickle file for DC is that we want the design compiler to understand these constraints and to generate a netlist for us, which will be a best optimized netlist that the IC compiler can consume and work on it. So the whole intention of providing it here was to get the best netlist out of DC that suits our constraints. Then we compile the design, and we print some outputs when it is done, and finally we write the Verilog file, which is the netlist of the corresponding RTL file, and it will be saved in this location. In fact, this location, I've changed this location after, I've changed this location. This location actually corresponds to CTS_clock_plot. So this will be the location where it is saved to. Even though I changed it here, I already have the Verilog file at that location. So CTS_clock_, okay, that's the output work. CTS_, yeah, this is the Verilog file. So I already have it over here. So this is the one that the DC has produced. So this file FIFO.v, it is the same file. So now we are done with DC, and it gives the cells and the references and the libraries and its attribute used as a result of it. So yeah, it shows that it cannot open the file because there is no folder like CTS15 right now, but I have done it before into the folder that I showed. So that is the reason you can actually ignore it. So pretty much we are done with the DC as of now, and the next thing we'll be doing is we'll be Switching to the IC compiler. Okay, so we'll start with ICC. So this is the command to launch the 2016 version of IC shell. Okay, so before running IC shell, we have to set up few files so that the IC compiler can successfully work on the netlist produced by the DC compiler. So first of them will be the setup.tcl file. This actually sets up all the parameters that we need, the paths and the libraries and the references we require to successfully generate a netlist, a schematic, an optimized schematic out of the DC output. So the first command is setting this my Milky Way library to this path. So this is the file or the folder that we talked about in the DC. So it just sets the path to this Milky Way library, and this second command also sets the MW path to the corresponding path which is mentioned over there. And next we specify that text file. The text file is a file where we obtain the physical library information from, and as compared to the Milky Way reference library, where the Milky Way reference library gives the physical information about standard cells and macro cells in your logic library. As compared to that, the text file that we are defining right now, it provides technology specific information such as name and characteristic of each metal layers. So we are setting it here. So the next comes the TLU plus files. The TLU plus files are actually binary table format that stores the RC coefficients. When we are generating the schematic by interconnecting all the cells, we need to be aware about the RC effects. So TLU plus files contains all the information regarding the RC coefficients. It's used for the accurate RC extraction results by including the effects of width, spacing, density, and temperature on the resistance coefficient. So while specifying the TLU plus files, you have to mention a couple of, in fact, three other files as well, which is the maximum TLU plus mode file, which corresponds to the maximum RC coefficients, and the minimum TLU plus files, and the mapping file. The mapping file actually maps the metal and via layer names in the Milky Way tech file to the layer names in the interconnect technology format file. So it is basically used for interconnecting all the cells, and all the coefficients and parameters that we need for successful and optimized interconnections are set using the TLU plus files. And this is the top module of our RTL design as well as our netlist design, FIFO1. So if you open it, you can see the top module named as FIFO1, and this is the Verilog file that we'll be picking up, which is the output of the DC. This is the path that I showed you when we are successfully done with the DC compilation. So this DC output will be picked up from this location, and it will be set up for the IC to consume. Along with that, we are defining the power, VDD, VSS, and the ports, and core utilization and core space. It is not really important to give this here because we'll be changing it, tweaking it again in the floor plan process. So this is the setup.tcl file. I'm going to source it. Because the files are in this location. So I source it. So it gives a couple of errors. It says that the Milky Way design and the library is not defined because we are trying to close it when we start the file. There is nothing open, so it gives the error, so you can ignore it. Going on, we'll be doing the reading process, the read article file, and we source the setup.article file. Again, here it basically does the same thing, and we do the search path appending and link library, target library, and the Milky Way reference library, which I already explained. Yes, and this deletes any Milky Way library which is already present, and it imports the Verilog file that we have defined in the setup file. And these are the same constraints that we gave while generating the netlist from the RTL with the DC. I provide those constraints again for the ICC. Earlier it was provided to the DC. Now we provide the same constraints for the ICC as well, which is supposed to meet our general specifications. So it's the same thing. We provide it again in read article file, and we run the command. And this is used to override the design that we currently have. So we have run the setup, and now I run the read article file. Okay, so it says that the maximum capacitance constraint is too small over here. It gives a warning. That is because I've applied a capacitance constraint over here. So as set clock tree options. So I can take it out. I just don't need it right now. I can rerun it. So now everything is clear. We are good to go. So the next process for the ICC will be floor planning. So if you we can open this GUI for this process. So this is the state of our ICC designs process, where we have like almost all the cells that we need. It has mapped all, it has understood the netlist that DC gave, and it has collected all the cells that we need to successfully arrange it and optimize it into our ASIC chip. So if you look below, it shows at the very bottom of the yellow display, it shows 1 by 100 plus. So there are like 100 plus cells. I mean, actually much more than 100, but it shows it all randomly put on top of each other. So it's all collected and it's all present over here. So the next stage will be the floor planning process. So the floor plan article file, it sources the setup file so that we get all the paths and the variables set in that session. And we open the library file and we copy it. We copy the Milky Way this design file, and we open it because we'll be now doing the floor plan. And this area, we set the core space as 10, which I will show you later once we are done with the floor plan. It actually keeps the area of the core from the boundary, and so the core utilization is given as 0.7, which means we want our design to have an core area utilization of 70%. So we are setting it right now while during the floor plan. And there is another constraint that we have. All input ports are located. Okay, the parameter 0.7 was fixed based on this constraint, and there are a couple of other constraints, like all input ports have to be on the left side and equidistant to each other, and all output ports are on the right side and equidistant to each other. So in order to achieve that, I set this parameter input ports as an output of this, because this command get ports it sets the input ports as a combination of all this. These are our input ports for the FIFO design, and these are the output ports for our FIFO design. And I use a set pin physical constraint commands to set it. Side 1 means that all the inputs will go to side 1, which is the left side, and this will be the width and depth of each port corresponding to each input, and we'll be using metal layer M3 to build them. Same applies to the output ports as well. We provide width and depth. Only difference is that we are placing it on side 3, which is the right side. And we use a create floor plan command to create the floor plan. So there are actually a couple of ways to do it. Either I can provide a fixed width and height. I'm not doing it because I want the IC compiler to compute the area depending upon my core utilization, because if I've given 0.7 here, I want an area utilization of 70%. So the compiler will automatically calculate what area it requires and what is the dimensions required for the ASIC depending upon that. Since it was not a general requirement for us, we decided to go with this command, let ICC compute the total area and the physical dimensions of the chip. So we do that. And this is used to derive VDD and VSS, which will be the power supply to the chip, the ground and the supply. And derive PG connection, we derive the connection to whatever we have done till now. And the next we'll be creating the ring pads. We'll be creating power rings, and this sets the width of the power ring to one unit. And the offsets, there are 2 offsets because we have 1 ring for VDD and 1 ring for VSS. I'll show this once we're done with the floor plan what 2 and 4 is and 1 is. And we'll be creating rings which runs horizontally and vertically. We'll be using metal layer M5 for the horizontal ring and M6 for the vertical rings. So these are the commands to create the rectangular rings running horizontally and vertically for VDD and VSS depending upon the parameters and the widths and the offsets that we have set above. And this creates a ring which runs through the corners of the chip. In addition to that, in order to ensure uniform power distribution, because we'll be placing cells within the depth of the design, so we cannot draw power lines all the way from the corner. So in order to provide better power distribution and to avoid congestion, we'll be using power straps which run vertically, which will connect to VDD and VSS as well. And I've given offsets as to where they should be present. They will have a width of 0.5 units, and they start at this location, and there will be 11 power straps for both the VDD and VSS. The VDD starts at 14 and it increments every 10 units with a width of 0.5, and VSS starts at 16 coordinates and it increments every 10 with a width of 0.5. So next we do the create FP placement. We set the placement strategy for this particular design to be having the macros on the edge as on, so it'll optimize the design better, and we'll provide the sliver size as 10 and the keep out margin with respect to the boundary, the hard macros as 2222. And we provide the strategy over here, the timing driven strategy, and we do is we legalize the placement with a medium effort. We have to ensure that once you have put all the cells that they are placed legally, they cannot be on top of each other, they cannot overlap, so all such things. We legalize the placement over here. And a write floor plan, it basically writes the floor plan into the file that we have mentioned over here. So it is just an output that we generate after the floor plan process. Once we are done with it, we save it, and so that we can go to the next stage of ICC. So before that, I'll run the floor plan script. So it'll take some time. In the meantime, we have the top layer blinking. Top corresponds to the fact that we have opened the GUI. So we have something like this as of now. And these are the horizontal and vertical power rings that I mentioned. The blue one will be metal layer M5, and the pink one will be metal layer M6. So we have ESS and VDD both running vertically and horizontally. And if I zoom in a bit, here you see the power straps that we have generated for even power distribution. So I can take the ruler. So you see that a 10 unit difference between the boundary and the core. So that is what we have given in the read, upfront for the floor plan. We have mentioned to keep that space over there, the core space. And each power rail has a width of 1 unit. I guess it was 1 unit. Yeah, the ring width is 1 unit and the offset is 2 and 4, which means that the distance from the core, the distance of the straps from the core is being mentioned as offset. So one will start at 2 and have a width of 1. The other one will start at 4 and will have a width of 1. So basically it extends from 2 to 3 and 4 to 5, as you can see over here. The same applies in the vertical strap as well. And that is what we have set the floor plan to be. And if you count it, you'll have 11 power straps running vertically. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 power straps. And the ports, all the input ports are on the left side and all the output ports are on the right side. And we have given the VDD and VSS connection. Another thing to be noted at this stage is that we don't have any connections. We just have the cells over here. They are just placed. They're not connected because we haven't routed it. We haven't done the clock tree process, which we'll be doing in the next step. So going on to the next step, we'll be doing the placement process. So it will source a setup file for the parameters, and we'll have all these parameters to be true, 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 and true, because we want to enable recovery and we want to remove the clock conversions, and we want the FISOpt. All these things we'll be setting when we do the placement process. And we'll be setting the buffer optimization strategy to be medium, because we'll be putting in buffers in between in the process, and we'll be doing it at a medium effort. And we set all the parameters, and this is the placeout command that we'll be running on. And we provide the preferred routing direction. We mentioned that M2 and M3 layers should be routed vertically. Should be routed vertically, and M3 and M5 should be routed horizontally. And we'll be ignoring this layer, minimum routing layer of M2 and maximum routing layer of M5. So we save it over there. We don't do anything other than placement in with the script. So we'll be running it. So it does the place opt command and it comes up with an optimized placement after many iterations. So that is still working, so I won't be able to open it until it's done. Okay, so in the meantime, while it is running, we'll go on and elaborate the next step, which will be the clock synthesis and the routing step. So I have made my own tickle file, which is a CTS clock tickle file. And the same thing again over here, we'll be setting the link library, target libraries, and we'll be sourcing the setup.tickles. We'll be opening the design that we saved in the previous step, which will be the place of saved. And we'll be running the clock opt, which will be the clock tree synthesis command, which optimizes the synthesis process in terms of routing, clock routing, and power, and basically everything related to clock tree synthesis. And we again mention the PG connection over here. It is not necessary to mention it, but we mention it. And once it is done, we derive the connections again. And we pre-route the instances of the components that we have placed inside the cells. And then we pre-route the standard cells. Basically, we connect all the power to the power from the power rails or the power rings to the cells. So we connect all the cells and supply them to VDD and VSS. That is what we are doing in the pre-routing of standard cells, and we verify it. It generates a report. I have not directed it to any file, but we'll be doing it later here. So after the cells are connected, we do the routing. We do the routing using the route auto option, and then we'll be optimizing it. And once the routing is done, we'll again be deriving the PG connection. And this step over here to derive the PG connection for all the VDD and VSS nets is very important, because if you don't do it, it will create shorts throughout the ASIC chip. When we run the LVS script, we'll be getting a completely shorted chip. Why it happens is that during routing, it will again move the cells a bit. It'll shuffle it a bit in order to get the best routing possible. And once you do it, it disturbs the PG connection. By PG connection, I mean the power and the ground connection. So we have to do it again. It may short something. So in order to be sure that everything is fine after routing and all the power is perfect, we run these two commands. And these two commands shouldn't be missed. It has to be present at the very end after all the process is complete. Then I generate a set of reports that I need to analyze what has happened, what is happening with my chip with respect to the timing. I run different flavors of the report timings, and which essentially gives me data regarding the timings. And I run the QR report QR, and I run the verify LBS, I run the verify route, PGNets, a set of commands that I feel that I need to look into. So I guess the placement process would have been complete, and we are currently over here. And if I zoom in, it's still not routed because we haven't ran the last script. It has placed it with an optimized strategy, so it is different from what we had before we ran the command. So now I'll go and run the clock tree synthesis as well as the routing command. So this is the tickle file that I was explaining, and okay. Okay, I yeah both okay yeah both are the same file. I had a bit of renaming process before the session started, so both are basically the same file. So I'll run it. Okay, so that tickle file has run, so we have done with all the process and we have our chip as of now. So it looks like nothing has changed, but it's not the case. When you zoom in, you can see all sorts of routings, all sorts of connections happening. I can zoom in and I can see the cells which are being interconnected to each other and to the power rails. So we get a clock tree synthesized and optimum routed design. So this will be our final chip, and we verify it by running the LVS verification. Okay, when we do it, we get an output. There is no shorts, there is no open, but we get some floating points. Floating points. If you analyze it, it says that Q the output Qn doesn't connect. Qn is nothing but Q bar of flip flops. Sometimes we may not need the output, so we won't connect it, so it stays unconnected. That is what it has been reported as a floating port, which you can ignore as of now. It's not an issue because we are not taking a connection from it. So we verify it. And one more thing that I would like to tell in the clock tree synthesis, since we are focusing on the CTS part. Okay, so we'll be exporting this design, the netlist, as a Verilog file so that we can do the formal equivalence verification. And I save it into this location. It's already present here, so I save it here. I already have it, so I don't need to save it. So that's how you do it. We export it into a Verilog file so that we can do the formal equivalence verification to ensure that our initial design is consistent with the final design. And this can go to the foundry and we can generate it in a corresponding format as well. So once we have it, we use the encounter conformal tool to verify the formal equivalence verification process. So I have to do some steps to read them in. I'll do it one by one. So this is the system Verilog file we had. We defined the root module here, which is the top module, and this is the golden type, which will be the initial design that we started with. So we load it here. It got loaded. Next, we take in the output of the IC compiler. Before that, we need to map the library that we use for it. Without that, it will give an error because we have an output of an IC C and it has all the cells in it. So the tool needs to know which cells it used. So we map the models, and we have used this library for it. The HVT library P95V125C, and this is a Liberty file, and it has to go to the revised version because we'll be comparing the golden version with the revised version. So I add it and I load it over here. It got loaded successfully. Next, I add the output of the IC design, IC compiler, which was stored in this location. FIFO, 4 work. 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 So this is the output that I saved at the very end of the IC compiler stage. It's in Verilog. It will go to the revised section and it will have a top module of FIFO. I add this, I load this successfully. Then we do the LEC and we get a table which compares the golden and the revised statistics. And to have a deeper look into it, we run the compare process. We compare them and we take the statistics, which will show that the golden design, which is our RTL, and the revised design, which is our output of the IC compiler, it matches with respect to inputs, outputs, and the key points that it has been compared. So it means that we have successfully done the backend synthesis process of it. We'll continue with further options of CTS.
So as Melvin mentioned earlier, that this is our clock opt and routed design, and what clock opt actually does is it does the clock tree synthesis, routing of clock nets, extraction, optimization, and optionally holds time violation fixing of the current design. If the clock tree synthesis or the routing of the clock tree net fails, the command returns with a value of 0, but it returned with a value of 1 in our case. So this is our final routed design. And for clock tree synthesis, we have different flavors of clock tree synthesis, and so I will show you the commands that we can run. So this is the basic clock opt command that does the clock optimization, and apart from that we have different commands like clock opt only PSYN, which performs only optimization of clock, and it ignores all the other results and other options mentioned in the tickle file. And then we have other instructions that we can perform with clock opt that optimize the DFT, so which enables the clock aware scan reporting. It tries to minimize the number of buffers crossing in the scan chain. Minimizing that can reduce hold time violation. The scan-def data must be loaded in that case, which defines the scan chains before clock optimization, which I did during my iterations. We have other instructions like concurrent clock and data. So when we run the concurrent clock and data instruction with the clock opt, the tool synthesizes the clock tree, performs data path optimization, and computes useful skew for improving the setup of worst negative slack and total negative slack, and performs the addition of data path optimization. And apart from that, we have different options like incremental concurrent clock and data, which performs incremental data path optimization and timing improvement driven clock tree optimization. It improves timing of all active scenarios. In that case, if we have mentioned any exceptions or any specific requirements during our read cycle, then we have another instruction, update clock latency, in which it updates the clock latencies after clock tree synthesis is performed and after the clock tree optimization. The interclock delay balancing, if enabled along with update clock latency, and it performs the detailed routing of the clock. So, and the third instruction is self-gating. So if we have any clocks which are self-gated, it takes care of those clocks and it gives us the results. So when we run these iterations on our place design, we get different kinds of outputs and different results that you can see that we have run LVS and various other reports that we wanted to analyze after doing the synthesis, which are QR reports, timing reports of various kinds. So this is the compiled report of our iterations, what we did on our place design. So if we go through these, as mentioned in the requirements, we have all different kinds of extractions from the QR report, which mention the total cell counts and the areas utilized. So as you can see, for the only PSYN mode, I have this QR report for it, which shows the design's total was negative slack as 0.91, total negative slack as 8.02, and number of voiding nets as 15, whereas the design hold WNSs are 0, TNSs are zeros, and number of editing paths are 0 as well. Then as per the specific requirements, these are the combinational areas, non-combinational areas in the reports, and buffer and inverter shared areas for the file. And these are the cell counts, which are for combinational sequential cells, and along with that the buffer and inverter cells mentioned over here. So these are all mentioned over here in the reports, the cell areas, the cell counts, and the detailed top 5 setup path and the hold path reports are enclosed along with our submission in the deliverables. So these are all the different flavors that we have run. Along with that, we have another set of reports which are for clock opt and other options like clock tree, clock opt for clock tree and specific clock of W clock, then with congestion and area recovery, which fix all hold clocks, interclock balancing, no clock routing, only CTS. So basically these are all the reports which will put some more light on the flavors of clock tree synthesis. And now I will hand it over to Nancy so that she will be able to explain to you the exceptions and all other different kinds of options you can explore in the clock tree synthesis and ICC tools. Yeah, you can log out.
Hello, I'm Nancy and I'll be explaining to you the rest of the CTS options such as exceptions available for clock tree synthesis, and I'll be doing it through the GUI so that you can understand how to use the GUI for CTS. So the first the CTS allows 4 kinds of exceptions on pins. The first is a stop pin. The stop pin is any sync pin which is at the end of the clock tree. So any sync pin by default is a stop pin, which means that the delay and any kinds of timings are balanced between the clock source and these points. So the Synopsys ICC allows you to place exceptions on these pins. So I begin by running just the clock opt command as given here, and then obtaining the sync groups. The sync groups are pins which begin at a root, and the routing goes on till all the syncs are reached. So in this case, on reporting the sync, I found that there are 3 syncs for the 3 clocks that we have given: R clock, W clock, and W2X clock. So the sync groups gives you the longest path and the shortest path on each of these clock paths. So I have selected these long paths and given an exception on these pins. pardon me. So as you can see here, I've created a CTS file where I'm setting clock tree exceptions on pin number 7, reg 7 for clock 2x, this for clock reg 36.2 for clock W2x, and Arvin reg for clock R clock. And when you generate the report for these, after running the CTS, you find that an exception has been placed on these pins. So if you look at the report for exceptions, you can see that an explicit sync pin has been defined. We must also keep in mind that all the sync pins by default are all the pins are considered as stop pins. All the sync pins are considered as stop pins, and here we have explicitly mentioned a stop pin. So if you look at the CTS TCL file, you can see that I have used the command report clock tree exceptions to generate the exception report. So if we go back to the GUI now, we can see that the GUI has been generated. So I'll be showing to you how the clock routing appears after the entire process has been completed. So we'll go to clock, and in clock we'll be going to color by clock trees. So right now a clock has been loaded. I'll reload it for your convenience. I'll be selecting W2 clock, and I'll be showing you the two levels it has. Actually, I'll show you all the levels. And any buffers that might have been placed on the way. So as we see that since W2X clock is only used for driving the inputs, it's mainly located to the level 0 where there are two pins. It is mainly located to level 1 where it is connecting to 8 different pins, and at level 0 the whole routing is being done. So as you can see, the levels indicate the connections or the buffers that have been placed from the clock till the pin. So as there are no buffers, as you can see here on the right side, the 0th level is the clock from the root, and the first level or the second level in this case is the connection to the pin. If we move on to a different clock, let's say W clock, and we enable the buffers in this case,
Pardon me, it seems I haven't selected all the options. So if we go here, I'll select the buffers. So WCLK is a clock which goes to majority of the modules, and this will have the biggest routing of all the 3 clocks. So since it has 3 levels, it will be easier to show you how the levels work in a clock tree synthesis. As you can see, the yellow is level 1 followed by level 2, which is pink, and if you zoom in, you can see that the level 3 is a connection to the pin. I can show you a couple of them. See, as you see, these the third level is the pin itself, and if we go here, we see that the yellow line converts into pink, and there are buffers there. So the level 1 connection comes in here, and from here the level 2 connections are taken out. Now if you open the interactive, if you go to clock and open the new interactive CTS window, you can select a clock and view its abstract graph. So as you can see, if I double click on these, I can see the 6 buffers branching out and the sync pins connected to each of these buffers. So if we go and zoom in there, let's zoom in and see the buffers. So you can see one of the buffers that's connected, and from here about 60 pins will be coming out. So since this is the only clock, W clock is the only one which buffers inserted. So if you move to a different clock, you won't be able to see any buffers, but then you can see the fan out of about 20 from the R clock. That is the interactive window. Now moving on to the next exception option, I'll show you the set clock tree don't buffer nets, and I have given the option of not buffering nets to the W clock. So you see that W clock is the only clock with buffer on it, and when I give this option, my design changes. This design changes and I only get one layer of routing. I will load the other design and show you how the clock tree synthesis has changed. As you can see, the synthesis is done. We'll go to the design and see how it looks. So we'll be going back to the clock and we'll be viewing color by clock trees. And as you can see, this tree has been loaded by default. So once we reload the W clock, we see that even after selecting buffers, there's no buffers available, which means that the whole routing has changed in order to include this particular exception of not having any buffers on the W clock. So that is all about exceptions. I'll be going to the next part, which is verifying the clock tree. So after running the verify clock tree, after running the clock op, you run the verify clock tree option. Which provides this kind of a result. So one of the options which is available with ICC is that it gives you solutions if there is something wrong with your clock tree. As you can see here, there are a couple of warnings but nothing major. So it tells me that towards the end that the solution file is empty because there is no solution provided, as the clock has been properly routed and all there is are some warnings related to capacitance.
So we can show you that after doing clock tree synthesis and analyzing different types of clock optimization options, that there are no skews in the circuit. So if we are doing any
high performance designs of like which has more kind of sequential circuits or flip flops, we get some kind of skew, and we can remove these cues from the design using fine tuning and all of the different options which are available in the ICC tools. So for all those fine tuning instructions, we can always man the commands, and we can get to know what are the different types of fine tuning options we have to perform the skew removal from the design, and so that we can continue with the conformal tools for formal verification, and so that our design will be ready to go to the foundry. So this was all about our presentation. Thank you.